In this lecture, we're going to talk about the most popular learning algorithm called deep learning, which is also known as deep neural network. This is the advanced form of the artificial neural network we talked about last week using, for example, backpropagation algorithm for training. And we're going to be using the same backpropagation algorithm for training deep learning or deep neural network. The latest hype on the recent drastic progress in artificial intelligence has been attributed due to the advancement of the deep learning algorithms. Okay, so we're going to try to follow the this outline. For example, why deep learning and what are the advantages? And we're going to also talk about a couple of the representative DNN models for applications. And particularly, we're going to go through the most popular deep learning algorithm called CNN, convolutional neural network, as well as RNN, recurrent neural network, also known as LSTM. Now, this one actually has different names now, also GRU, or gated recurrent unit, or even today, which is called transformer. So they all have connotations having to do with sequential data set for training. And then we can also talk about GAN, which is a type of a deep learning model for the purpose of synthesizing data sets. So would be very useful for the data augmentation. It's called the generative adversary network. Okay, so because of once again a big hype on the deep learning with a lot of success stories, there has been a slew of references and other resources for the purpose of developing, let's say, codes for different type of applications. So here are some of the references that you could look into, especially, for example, like CNN models and RNN models. Uh, the the de facto language for developing code would be that of using Python. But these are some of the toolboxes, or I should say, a set of libraries that could enhance much easier way of developing codes in deep learning. For example, like Keras, TensorFlow, and PyTorch. They're all open source, so you could actually download them by visiting these sites. So what are the differences? Well, Keras to me would actually be well, it is capable of running on top of TensorFlow, and to me, I think it's got a lot better interface structure. So Keras would be the one with a little bit higher level of language compared to say TensorFlow, as well as that of PyTorch. The advantages of using TensorFlow and PyTorch would be that because of the fact that they're a little bit more, I guess, getting deeper involved with the code to a lower level language level, that the speed of would be much faster using TensorFlow or PyTorch. As far as the popularity is concerned, there's been all these three library sources are actually being increasing in terms of popularity. Keras has been actually leading the flock, but PyTorch also is catching up very fast. Especially nowadays, I think PyTorch has been de facto, I guess, best player in the arena of Python libraries for deep learning. Well, one of the reasons why deep learning algorithm has been um, very popular is because with the size of the data set or the training data set increasing, the performance keeps increasing. Whereas for the traditional machine learning algorithms, that there seems to be some sort of a ceiling that it does not go improve any further than a certain threshold. So as long as we have increased amount of the data set for training, deep learning algorithm would actually continue to increase its performance. Now, one of the advantages also having a data set size increase is because we can also solve the overfitting problem, which has been a very uh, a primary reason why, for example, in the early 90s, artificial neural net with the limited amount of number of the parameters actually could hit the um, limitations and because of the overfitting problem that it has. But on the other hand, compared to, let's say, artificial neural net, the traditional machine learning algorithms also has this ceiling in terms of performance, even though the size of the data set continues to increase. So this is actually the choice, the de facto choice nowadays for the purpose of developing, working, let's say, machine learning algorithm is by using a deep learning algorithm. Okay, for example, in the supervised learning application, the traditional models actually, which uses handcrafted features, would actually be encountering, as I said, a lot of limitations. Now, let's look at the the difference between the handcrafted features versus that of the way how the deep learning features progressively develops these features by learning process. Here, for example, let's say that we have an image of a dog here. Let's say that we want to develop a code or software or an algorithm that classifies that into either a dog or say a cat. Let's say some binary classification. So what's going to then need is some sort of a feature that would represents this dog, and then let it go through a classifier to perform an output decision on the output. Now, if you look at and zoom into the handcrafted features, the way traditionally, that people have done is to look into the image and see which or how the good features could be actually extracted. The good features for, once again, for the trainable classifier. So, for example, in this case, people they did was that they would actually subdivide the image into smaller, say, patch, and each of the patch, and particularly that of the key point locations. What people have done was to, for example, apply this SIFT type of descriptors. SIFT means scale invariant feature transformation. And there are other type of descriptors like this, making, for example, the object, in this case, particularly that of a dog, we want the classification to be independent of the scale or the size, independent of the orientation or the direction, and so forth. So we want descriptors that could actually work, making it independent. Um, and so we traditionally let it go through a lengthy steps so that the features that in the end that is defined or extracted by going through the very lengthy and tedious handcrafted feature process is so that we could then inject it into this trainable classifier. Now, so the problem with the handcrafted features is that the process is very tedious. As you can see here, this takes up the entire multi steps to generate into the features for the purpose of using it as a trainable classifier. So it's going to actually cost a lot to develop handcrafted features. And also at the same time, we need to have like different type of sift or different type of visual word type of process in between, depending on the type of application. So this is going to be very much application dependent as well. On the other hand, for deep learning process, the features are actually learned by itself from, let's say, stage to stage. There is a built-in automatic multi-stage feature learning process that learns this rich hierarchical representations. For example, if you have an image like this, and let's say that the purpose is to say, once again, a binary decision being outdoor versus indoor, then this deep learning model having a multi-stage feature process, starting with a low-level feature to the mid-level and then a high-level feature, it goes into this sequence of representations where, for example, the low-level features would be an abstraction of the original data, and the mid-level feature would be an abstraction of the low-level feature, and so forth, as it progresses toward the trainable classifier. So what is a low-level feature? Well, the lower-level feature, an example of that is given here, that with the original image being defined with the, say, pixels intensity and, say, 3 different color channels, the low-level feature would be very close to the pixel values, whereas for the mid-level, it could define, for example, like the edges, the corners, and so forth. And then further mid-level feature after that might be, for example, giving like the texture type of representations, and then finally the high level features would actually give you the more or less the shape information. And then at that level, the high level feature would be sufficient for the purpose of having this trainable classifier to be applied, thereby being able to perform this classification much easier and robust. So I just talked about the process of deep learning using image as an example. So from the pixel level to the edges, to the texture, to the motif and part and the object shape and so forth. You could also do the same for, let's say, in terms of a text type of input process, where at the different levels of feature, text would be, for example, at the low level would be that of a character, the mid-level feature would be that of the word group for the one higher, and so forth. So at the very high level feature, you could actually have a story then, which could be used to as an input to the trainable classifier for the purpose, once again, for classification and so forth. So here, each module in each of these level features in deep learning transforms its input representation into a higher level one in some hierarchical process, which is very similar to the way how human cortex, the brain cortex, actually works. Okay, so having said that, let me give you an overview of what some of these deep learning models that we have today looks like. So to me, I would say that you could actually categorize the deep learning models into one having called multi-layer perceptron, which is exactly the artificial neural net that we talked about last week. So this would be an extension of the artificial neural net having multi-layers, not just one or two shallow hidden layers, but more than that. Let's say 5 or greater hidden layers, but having this type of structure. So in this case, this would be useful for static input-output mapping. For example, like we have some static images, like snapshot of an images, for the purpose of let's say handwritten character recognition or classification. So this would be a very handy, I should say, a network or a model that could perform such classification. And similarly, there's also one that's very close to that is called the CNN, or convolutional neural network, which is also very useful for a snapshot or a static type of an input for the mapping, as once again output being some sort of classification. So here, once again, in this case, would be like that of performing, say, classifications onto handwritten characters. And the way how the convolutional neural network looks like it looks like this, which is composed of a two stages of process of multiple steps. One, for example, convolution, and then we have a sub sampling or pooling. So you have, hierarchy of both the convolution and pooling or subsampling as a unit, as a pair. And then with that combination, you have more set of such pairs that comes afterwards. And essentially, toward at the end, there is a feature. There is a say final feature that goes into performing, just like here in the multi-layer perceptron, some sort of a multi-layer perceptron type of an architecture in the end. So to me, what CNN does, which I'm going to talk about that, by the way, a little bit more detail after this slide, is that for CNN, to me, it's actually feature representation process. So feature being, as I said, that goes through the convolution as well as that of the subsampling in a pair, and then eventually it reaches to the final form of feature, which would be, once again, a desirable form for the purpose of then using it as an input for which then would be fully connected neural network here at the end for the purpose of classification. On the other hand, the third category that I want to that I have here is called that RNN, or recurrent neural network, also known as LSTM, long short-term memory. There are other names like GRU and so forth. Where typically this would be this could be used for dynamic input-output mapping, meaning that the type of input that we have here would be a sequential data, for example, like time series, or maybe how spoken language would be uttered in sequence. For example, I go to school, which I said that here I say I being subject and then go being verb and the school being like an object and so forth in sequence. So that type of linguistic process, which takes representations over time, could be mapped by this recurrent neural network type of structure. So this is something that I want to also talk about as part of the lecture. And then we have a combination of static plus dynamic input-output mapping process. So here, for example, we have an example of this type of representation would be useful is when you have, that's an image that you want to describe with a, say, closed caption. Then an image would be a static, and then the description in terms of, say, a sentence, that would be a sequencer data. So combination of the two, one, the static represented by, say, CNN or convolutional neural net, and the sequencer data represented by RNN could be useful for performing, let's say, image to closed caption or captioning type of application. Okay, so let's look at the motivation for the purpose of, let's say, developing convolutional neural net. If you look at a simple artificial neural net or MLP, multi-layer perceptron, it looks like this, right? Well, I should say this is much less than just multi-layer. This would be even though this is multi-layer with having a hidden layer, this would be very much shallow neural net. So with that, we have, as you know, as you can recall, we have an input unit, and it goes through a hidden layer unit. And then you have the output, where the output actually generates the prediction based on the learning process, where the learning is done by having these weights or the parameters updated by means of backpropagation. So typically, the way how we can recall is that, for example, these hidden layer neurons would be particularly using, say, a sigmoidal or some sort of nonlinear function, where this nonlinear function is mapping over the regression, the linear regression formula, which is essentially a weighted sum of the inputs, where the weights are represented by the parameters. And these are the ones that would be, once again, iteratively converged to some final value by going through the training process. And well, actually, yeah. And then we have the second layer, which is the output, where the superscript 2 here represents the layer number. So we have the same, for example, or maybe it could be different, say, nonlinear function. In this case, we say it's a sigmoidal function, which is also called, by the way, softmax, is another way of using or describing this sigmoidal function. And so this nonlinear function is once again a map over the weighted sum of the input, where the input in this case, for the case of this neuron, would be the outputs of these the previous neurons, a previous set of the neurons from the previous layer. And the activation function, or the nonlinear function, is typically either a sigmoid or ReLU, where the ReLU function, as you can recall, would look like this. So this is, say, z and g of z here. So this would be, well, I should say, let's say g of z there. So anything that is less than z being less than 0 would be 0. And if it is greater than 0, then it's linear. Consequently, we can say ReLU would be essentially a max between 0 and that of z. Okay, well, so this was just a recall of what we have had in terms of understanding artificial neural net and how it is represented. Now, what I want to do at this point is to talk about the size of the parameters to represent and build such an architecture. So here in this case, because we have 4 input units as well as 4, say, neurons at the hidden layer, so the total number of these parameters, or the weights, would be between here and here would be 4 by 4. And then we have another 4 here, but this is 4 by 1. So we have 4 by 4, which is 16 plus 4. So 20 parameters altogether, or 20 weights that we need to update. Now, so that would be actually good and dandy if the input size happens to be very, very small, like the one that we just talked about. But if the input is an image, and a typical, well, actually, this is not even a typical nowadays. It's still very small. Let's say 400 by 400. So this is 400 vertical axis and 400 horizontal axis. And let's say that we have 3 channels, RGB. So that means that the total number of input dimension would be 480,000. So input unit by, once again, columnizing, by embedding all of these values into a single column, it would be 4,800 480,000 say number of units in the input. And suppose now we have say a identical number of the neurons at the hidden layer. So that means that the number of, just like the way that we've done for the previous slide, is to have to count all these connections or connecting, say, weights. Then that would be 480,000 times 480,000. And then we have 480,000 here. So this would be 480,000 times 480,000. And then we have, once again here, 480,000 times, say, 1. So that means that if you compute the product of this to this, and then you add this, that's going to be approximately 230 billion. So quite a bit of a big size of, say, weight or the parameters. Even if we let's say simplify the number of hidden neurons to say limit it to, let's say, 1,000. Okay, let's just say that rather than having 480,000 hidden neurons, let's just limit it to 1,000. Then even with that number, that's going to be approximately 480 million number of weights or the number of parameters. So it becomes huge in terms of, for example, in terms of the size of those weights that needs to be updated as it goes through the learning process. So therefore, the convolutional neural net becomes actually very, very handy because it sort of like alleviates the problem of having just too many parameters to be updated in the iterative process called backpropagation. So the convolutional neural net, in a nutshell, looks like this. This is that architecture. So it's got a very specialized connectivity structure. It is feed forward, goes this way, as well as the training is done just like the artificial neural net that we have talked about, or the multi-layer perceptron is done by using backpropagation. And now it's got a specialized connectivity structure by means of having, let's say, convolution, as well as some sort of nonlinearity. Typically, that would be, say, ReLU. And then it goes through the pooling process or subsampling. For example, suppose this is your input image, which is, say, small, 32 by 32. Then typically what it does is that it's got, say, a number of these, say, image patches called, let's say, filters. And each of filters would be raster scanned, going like this, and then develop a feature map. So each of these mask or let's say filter then has its receptive field, and that receptive field then moves from left to the right until it sort of like finishes at the bottom right. So you would have, for example, multiples of these filters. For example, in this case, you would have like 6 number of filters. So as a result of performing convolution, which I'm going to show you exactly what that is in the next set of slides, is that it's going to actually reduce the size of the feature map from, say, 32 by 32 into smaller, say, size. So you would have 6 different, let's say, filters applied, and then obtain the feature map. And then after that, what we want to do is, because of the size of the input is still relatively, it is small but still big because it's an image. What we want to do is to subsample it, which also is called the pooling process, so that we sort of like try to say decrease the size of the dimension. So So this 28 by 28 becomes, for example, 14 by 14. And so we have a pair of these goes once again. Convolution is done one more time, and then subsampling and so forth. So you could have like multiple stages of such pair: convolution, subsampling, convolution, subsampling, convolution, subsampling, and at the end there is this the finer feature, where the finer feature is then connected into a multi-layer perceptron, or it could be just a simple perceptron to perform, let's say, some sort of classification at the output. Okay, so why convolutional neural net? Well, because as we just saw, that the total number of parameters just becomes so huge if you just have the input, all of the input, in terms of, say, image, connected to the same number of the hidden neurons. For example, that would also be called the fully connected layer. Suppose you have an image. In this case, actually, this image is actually that of the acoustic signal. Put it into two-dimensional form called the spectrogram. So spectrogram might look like, say, 412 in, let's say, in horizontal axis, and then 80 in the vertical axis. Actually, the horizontal axis is 80, and then the vertical axis is 512. So this is like 80 because this has to do with time, and the vertical axis is 512. So this is a huge say a snapshot of an image. And if you have this identical number of neurons all fully connected, then that's going to be roughly about 2 billion number of parameters. So that's just too many, once again, number of parameters to deal with for, as we said, when we go through the backpropagation and then update the weight for convergence. So the other possible way of reducing, say, the number of weights is by using a smaller set of the hidden neurons. And the way we could do that is to have identified, let's say, certain neurons to be locally connected only. Let's say you have this particular neuron connected only this region, and this neuron connected only to having the receptive field only focused on to, say, this particular location of the original image. Then we are going to actually have much less number of the neurons to look into. And let's say that we have 40,000 hidden units to look into the local, say, local area or local receptive field of the entire say spectrogram image, then that's going to be still 4 million parameters, with the filter size being 10 by 10. So that's still a huge number. So the other way, a third way that we could actually do with much less number of parameters is by means of parameter sharing. Suppose you have let's say, once again, some sort of a neuron. Here, that neuron would be, once again, 10 by 10. And this neuron then has this particular receptive field. And then this has a so-called parameter sharing. In other words, you have the you have the connections, the connecting weights to be continuously shared as it raster scans from left to the right, and then all the way down to the last corner here. So in that case, then the number of the parameter, because the parameters are being shared, is going to be much smaller. It's going to be much smaller. So, yeah. On the other hand, because we only have just one neuron, so the type of representation from that of the original data set, the image, might be pretty underrepresented. So what we want to do is to, instead of having just a single neuron that has this receptive field and then performs this parameter sharing as it goes through the raster scanning, is by using multiple filters. So instead of using one, let's say we could have, say, filter being, say, 100 filters. So having 100 filters, then the with the filter size, each of the filter size being 10 by 10, the number of connections or the weights would be just 10,000. So 10,000 is much, much smaller than, say, 4 million or even 2 billion number of parameters. So that's the beauty of using a convolution layer, because we are actually sharing the parameters. So this means that using about 100 filters, all of the 100 filters essentially captures the essence or the characteristics of the image as much as possible. Okay, so just zooming into the convolution neural net, once again, it's got, as we said, that from the input side, the forward propagation looks this way, and it's got a series of pairs of the convolution and pulling, and convolution and pulling, and so forth. And at the last, say, stage, there's going to be some sort of a fully connected layers. It could be multi-layer, or it could be just even having a single layer and so forth. And at the end, there's some sort of a softmax or some sort of a sigmoidal type of function as the output. All right, so each of the process or the stages, here's a representation of that process going on. So if you have an input image that goes through the very first convolution process, meaning that you have some sort of a filter, this nonlinear filter that convolves with the image. For example, so if the convolution, one of the filter goes through the convolution, looks the resulting feature map looking like this. And let's say we have another. Let's just say that we also have another filter and performing another convolution. So this is going to be yet another feature map as a result of going through the second filter's convolution process. And at this point, by the way, the convolution is also and at the output of the convolution, or each of the let's say the pixel at the feature map then goes through the nonlinearity. And a typical nonlinearity is to use the rectified linear unit, or ReLU, where once again ReLU looks like this. In other words, any pixel value here at the feature map, if you have some sort of a negative value or anything that's less than 0, it's going to all become, say, 0. So all the negative becomes, say, 0. Anything that's positive is going to be just maintained as positive value. And then after that, it goes through the pooling process, so that the feature map is going to become actually reduced, making a little bit more blurred image, so that once again the total number of the features, or the total number of the connecting weights can be reduced. We can also go through some sort of a normalization process, so that the values would actually be, adjusted so that it's going to become centered as 0, and it's going to be plus and minus 1, or being less than plus and minus 1 value. Or it could be, say, between 0 to 1. That's another normalization. So the final, after going through multiple stages of these pairs of the process, including the convolution, then you have a feature map. So there has been a lot of work on developing or building, a very deep architecture of the convolutional neural net. Um, for example, like VGG net is an example where VGG net was developed by big industries, including say Google Net and ResNet. So they all have very similar architecture in that, for example, using let's say image at the input, it goes a sequence of these pairs of convolution and pooling process, convolution and pooling, and so forth. And at the end, some sort of fully connected layers. And similarly, you have the Google Net doing exactly like that. ResNet has some sort of a skip connections like this. So it's actually useful, better than, let's say, VGG or Google Net in terms of, say, some sequential type of data would be actually useful for ResNet, where the what the so we're going to talk about more of these later on, but I just wanted to say that some of the popular CNN models has very deep architecture, having multiple pairs of these convolution and pooling process. So let's once again zoom into the convolution process a little bit more deeper. So suppose once again, if you have an input image, what's a convolution? So as I said, the CNN has involves with pairs of convolution and as well as pooling process. So convolution is to have, let's say, a filter like this, and then performs convolution. Let's say a filter that's defined by this, where each of these components by the values here would be designed at this point. Let's say that, for example, if we have an input and then filter going there, then this would be the resulting convoluted image as a result of performing convolution of this filter on the input image. Now, of course, the specific values of the filter intensities, these values would be learned, and by going through the CNN's learning process using the backpropagation, their error at the very end is going to propagate back and then have these values become updated. So once again, this slide is trying to capture and show the convolution process. So for example, if this is your image, then this would be the receptive field by, let's say, a very particular filter, which is defined by 2x2 filter size. So the convolution process is essentially to have this guy, the filter, applied on top of this, making this as the receptive field, and then perform convolution. So that convolution is to have this weight value multiplied by this, and then sum with this value multiplied by this, summed with this value multiplied by this, and this guy multiplied by this, and then summed, and then it goes through a nonlinear function, and that typical nonlinear function, as I said, would be ReLU function. So whatever the value, the sum, the linear sum is going to be given, and then it goes through the ReLU value, and that value is going to be provided right here. So this would be H1. And similarly, if this thing goes to the next, let me use another color just to indicate that, for example, as we stride one unit to the right, then we have say the same filter applied to, let's say, this particular receptive field, and it goes through exactly the same process. In other words, it's weight multiplied by that, summed with this weight multiplied by this, summed with this weight multiplied by that, and then summed with this weight multiplied by that, and then the whole thing is activated using, once again, this ReLU function. So in this case, the number of parameters for one feature map, which is this, would be 4. And suppose you have, let's say, 100 filters. Okay, so you just not only have one, but you will have 100 filters. So here's 1, 2, 3, 100 filters. So you would have 400 number of parameters to map for one for representation by this convolution process. And then it goes through the second stage. So after going through, say, layer 1, you develop this, say, feature map. And then you also have the layer 2 going through using, say, second filter, where the second filter also performs, once again, using this receptive field and then performing convolution. And then convolution, the convolved value, the result is then goes through the ReLU activation function and so forth. So then it goes through the second layer feature map. So once again, each of the filter, the hidden units are connected to the local receptive field, meaning that this particular weight filter is all connected to the local field, the local receptive field, like so. And this thing just moves with a raster scan with a stride of either 1 or 2 or 3, depending on how you want to set your convolution process to work. And then after going through the convolution, then it goes through the pooling process. So what's a pooling? So pooling process goes through, it's essentially a subsampling process so that you could actually decrease the size of the feature. And there are a couple of pooling process. One is called the max pooling. The other one is called the average pooling, where the max pooling, what it does is that it searches for the maximum value within a rectangular field of the neighborhood, and that becomes the value, the chosen value that represents the entire rectangular field. Average pooling is similar. What it does is that out of that rectangular field, you compute the average value. For example, suppose you have here with the input matrix, and this input could be either image or maybe that of the feature map. Let's say this is your input image. Well, actually, I shouldn't say input image. This should be the feature map, because the pooling process actually takes place after going through the convolution. So when I say that it went through the convolution process, that's going to be essentially some sort of feature map. So let's just assume that this is a feature map. So it's a 4x4 feature map. What I want to do is to apply the pooling using the max pooling so that the entire feature map size becomes reduced. And the way it is going to be done is that I'm going to be using 2x2 filter with a stride of 2. So that means that here this is a 2x2 filter, and then using a stride of 2. So this is going to be moved to the next set by moving 2 units to the right. So this one here, out of this, what I want to do is to look for the maximum value. So out of here, the maximum value happens to be 4. So I write 4 down here. And then the next set of the filter, 2x2 with a stride of 2 would be right here. And then out of that, the maximum value would be 5 right here. So I put 5 down here. And similarly, the lower left, you have 3 as the maximum value, and the lower right, the 4, value of 4 is the maximum value. So this 4 by 4 now reduced down to 2 by 2 as the filter map after going through the max pooling process. Okay, so overall, by going through once again as going through a combination of the convolution as well as pooling process, where the pooling is the red color, and then you have the filter being the convolution of say 2 channels. This is 2 channels, 2 channel here, and the 3 channel, and so forth. And then eventually it goes through the fully connected layers. And after that, let's say after this value here, which would be represented by this one here, would be all go through the fully connected output vector, where each of the output vector would be one hot a vector representing for each of these say class in terms of, let's say, the type of classification that you want to have as an output. Okay, so in summary, the convolution neural net is that the output could be binary, it could be multinomial or continuous, or it could be some sort of a count of the numbers. Input could be some fixed size, and it could be typically an image, and so forth. And architecture could be, it's an ad hoc, it's a choice that you can make. So what would be the best architecture? Well, it's going to require a number of going through different experiments to figure out which would be the one that actually works the best. How do we then compute or obtain the final output, the final, let's say, parameter values, is by using the backpropagation. Once again, we use exactly the same backpropagation, where the backpropagation works with this gradient descent of the error that propagates toward the front end side, as the way we've done for the artificial neural net or a multi-layer perceptron problem. Now, because of the way how the convolutions with different filters are mapped to the, let's say, feature map, because once again, having all these weights being shared as it performs this raster scanning or convolution taking place, a lot of the process is actually done in parallel. So it would be much better to use a graphic processing unit or GPU to make it much simpler. Because of this parallel connection type of architecture that the convolution neural net has. Okay, so that was about CNN. Now what I want to do is to talk about RNN, which is also known as a recurrent neural network. The advanced form of RNN is the LSTM, or the long short-term memory, where the long short-term memory, what it does is that it solves the problem of a vanishing gradient problem, or vanishing or exploring gradient problem. It's either vanishing or exploring, but mostly typically the vanishing gradient problem. In other words, if the let's say architecture, the network is very long, then typically the output, the error at the output does not propagate for a very long architecture toward the front end. So therefore, those weights that are very close to the front end side wouldn't be learning, or the changes or the updates on the weight becomes so small So to resolve that problem, we have a slightly modified version of the RNN called long short-term memory. Now, one that uh, also resolves the problems of LSTM is called gated recurrent unit, or GRU. And also nowadays, by the way, we use a transformer in place of RNN, LSTM, or GRU. So transformer is indeed the de facto scheme for capturing and mapping a dynamic or sequential type of data. Okay, with that, maybe I should